All right, so we're going to be reviewing from Astronomy Regents Review Part 2. Once again, base your answers to questions 11 through 15 on the information below and on your knowledge of Earth and space science. Some questions may require the use of the 2024 edition reference tables for Earth and space science, right? So, for number 11, we'll go. It says, which explanation about the cosmic microwave background radiation provides evidence for the Big Bang? All right, which explanation about the cosmic microwave background radiation provides evidence of the Big Bang theory, right? Now, remember, each type of question, right? You have two types of questions. Well, the first type of questions may be you may get your answer based on the passages, the reading, or graphs to draw a conclusion. Sometimes the other type of question is purely content, which is just information that you need to come into the regions with, right? So just by me scanning, and you can pause this video as well, even right now, but just by me scanning, right, I'm looking for keywords that mention anything about cosmic microwave background radiation, right? Don't see anything really, right? I'm guessing from the early universe. Nope. Nope. Okay, this telescope one of the first to record cosmic microwave background radiation coming from all directions in space. Okay, so the passage may not help you so much, but so that means that this is information that we need to come in with. So if you look at your note sheet, right, especially the Big Bang Theory summary, if you look in this section, and once again, you can pause right here. Cosmic microwave background is radiation that was left over when the universe cooled enough, right, about 380,000 years after the Big Bang, right? So that's a key important part, okay? Even in this note sheet, you'll also realize, right, that it gives us an estimated timeline. Big Bang occurred, right? When did the first stars appear? The early galaxies appeared, the solar system, and our present time. Okay, so this is information that we need to know coming in. Now let's do some process of elimination, right? So choice one, since the cosmic wave background radiation was detected coming from all directions, right? It must be evidence from multiple explosions occurring at the same time 13.8 billion years ago, right? We learned that there weren't multiple explosions, right? We just know about the Big Bang, and at that point, right, massive amounts of energy was released, right? Not multiple explosions. So therefore, we can cross this out. Number two, it says mathematical calculations show that if the universe began with a Big Bang, it would have released a huge amount of energy, right? It would have released a huge amount of energy, which I see right here. Is that the universe expanded rapidly and released energy. Okay. On all directions, it would be detected as cosmic microwave background radiation. It does match somewhat, right, to the information given on that last sentence, right? Cosmic microwave background radiation coming from all directions. So this is a possibility. So we're gonna hold off on choice two. Choice three, cosmic microwave background radiation is produced by every star and galaxy in the universe, which were created at the same time as the Big Bang. The problem is that it says produced by every star at the same time as the Big Bang. We know coming into this information, according to scientific theory, the Big Bang occurred, and many years later, the first stars appeared. Choice three is saying the Big Bang occurred and immediately stars appeared at the same time, right? But that information is false. Big Bang occurs And many, many, many years later, hundreds of millions of years later, we have the first stars that appear. So therefore, we can definitely cross out choice three. And choice four, the presence of cosmic microwave radiation is evidence for the energy released from dying stars that exploded in a big bang and created our present day universe. So they're saying that the Big Bang occurred from dying stars, and that is false, right? That is false. The Big Bang did not occur from dying stars. As a matter of fact, even when we see here, the first stars appeared, right, according to here, about 300 million years ago, right? So therefore, not, well, not 300 million years ago, it's much longer than that. But what I'm saying is that first stars had to appear here, right? And that occurred after the Big Bang, okay? So therefore, so about 300 million years after the Big Bang, all right? So that's why we can cross choice four, and that leaves us the best answer of point choice two. All right, so the second question, right, it gives us this graph, right? And so we want to make sure that we find out, okay, what is this graph even referring to? It says the only evidence astronomers have for the first stars that formed is the electromagnetic radiation they left behind. Telescopes like Hubble can detect objects billions of light years away, billions of years back in time. The graph below shows some information about the first stars that formed after the Big Bang. Okay? And so 12 says, describe how wavelengths of emitted radiation from first stars have changed, have changed, right? Since the Big Bang, and explain how this difference in wavelength is evidence for how the universe changed since the Big Bang. Okay? So the difference in wavelength. So since the Big Bang has occurred, right? What's one thing that I can say when I'm looking at the wavelength, right? What's one thing that I can notice about these waves, right? Well, one of the differences in wavelengths is that it does appear, right, for the wavelengths have become longer or greater, right? We can see that. Okay, it seems as though that the wavelengths have become longer or greater. And if you look, I encourage people to look back into your notes, all right? Because if you see, when we're talking about wavelength long and short, right? This is represents wavelength of light, but you'll notice how blue light, you see how the cycle repeats itself at a shorter distance than compared to red light. You see how it looks as if the cycle takes longer to complete, right? So that is an example of, hey, this red light has a longer wavelength, right? It takes a longer distance to complete one cycle than it does for blue light, right? A shorter distance to complete one cycle. So that's one of the concepts you do need to know coming into this, right? Now, how did the universe change as a result, right? If our wavelengths, when we're noticing from the light that has been emitted from the first stars, if we notice that the wavelength is increasing and increasing, this is a concept back in our notes that we've learned about the Doppler effect, right? And it says Doppler effect describe how waves change depending on whether the source is moving towards you or away from you. So one of the things that we notice is that we notice that a lot of the surrounding galaxies, the waves are stretching, right? And this means, according to the Doppler effect, if we see that the wavelength is increasing, we call that a redshift. And that generally means, as it says here, that galaxies are moving away. Galaxies are moving away. So if we're looking around and we're seeing redshifts or we see an increase in wavelength all around us, then that means that the entire universe is expanding. It's expanding at an accelerated rate, right? That means that all the galaxies are moving away from each other. And as a result, even what we see here, by observing the different wavelengths, all of these galaxies are moving away from each other, which makes the universe expanding. So you can say, how has the universe changed as a result of this evidence? The fact that we see longer and longer wavelengths coming from first stars, that lets us know the universe has expanded. All right? The universe has expanded. So this evidence shows that the universe has is expanding. All right, so we look at 13. It says, which statement correctly explains why the composition of Methuselah, a massive star, provides evidence that Methuselah is not one of the first stars formed during the Big Bang. So this is definitely a conceptual, and we can probably even use the reference tables kind of to help us too. So let's look at some background information about Methuselah, right? Methuselah, it says one of the oldest stars ever observed by HST is classified as a giant star called Methuselah in the Milky Way galaxy. It is believed to be almost as old as the universe itself. Based on Methuselah's composition, scientists do not believe it is one of the first stars. So, what is some information that we know about a giant star, right? And when we're talking about giant star, we're talking about more than just we're just calling it a giant star because it's big. The word giant star lets us know which stage of its life the star is in. So if we even let's even say from our reference tables, right? Let's even say from our reference tables, right? You'll notice, oops, let me flip this over, right? In all stars, right, they start as a huge cloud of gas and dust, right? Then temperatures become hot enough in order to nuclear fusion to occur, right? And something happens between the early stage or the main sequence stage to becoming a red giant. Something happens. What happens between a main sequence star and what needs to happen in order for this main sequence star to turn into a giant, right? Well, one of the first thing, if it's a giant star, that means that it was a main sequence star before, right? Which is one of the reasons why automatically we can say this is probably not an early star, right? Or we can say this giant star was something else. It was composed of something else before it got to this form. Now, in our notes, we learned that a giant star occurs, right, when the main sequence star uses up the hydrogen in its core, right? So at that point, we've learned, even in our reference tables, we could even look at page, oops, where we go? At 2, right? We know that the first stage of fusion is when hydrogen forms into helium. This is what's happening in the main sequence stage of a star. Main sequence stage of a star, right? Now, eventually, the hydrogen will run out. And when the hydrogen runs out, the star will now start to take helium and fuse it together to make carbon, right? This is the stage now where it starts to become a giant star. It's no longer a main sequence star, it is a giant star. right? That's why even when you look at your reference tables and you go to page 4, you see main sequence stars, right? Right here. Then we see giants or supergiants. In order for in order for a giant star to appear, the main sequence star has to be depleted out of hydrogen and start to take helium to form carbon, right? Once it runs out of hydrogen to make fusion, it begins to transition into one of these two paths. All right? So that's one of the first things. Okay? So now that we know that, it says, what is another, provide evidence that Methuselah is not one of the first stars formed during the Big Bang, right? Methuselah composition, more than likely, if it's a giant star, we're going to see helium and carbon. We're going to see helium and carbon. Well, what is some information we know about the first stars that appeared? And this was based on your notes. All right. If you look in your, give me a second. Let me pause here. Sorry. Give me a second. I apologize. Let me just pause. All right, when we look at our Big Bang Theory, right, it says that according to scientific theory, right, the Big Bang Theory in the very beginning produced about 75% hydrogen and 25% helium. All right, these were the two elements that was created, right, immediately after the Big Bang, right? Almost all of what was created was hydrogen and helium. That means the first early stars would need to have hydrogen and helium, right? And so that's why when I'm looking at my options, I see 25% carbon. That's incorrect. Methuselah composed of hydrogen, helium, and some trace of heavier elements, but the first stars contain a greater percentage of heavier elements. That is incorrect. The first stars were composed of hydrogen percent, 100% hydrogen, but Methuselah is composed of 50% hydrogen and helium. That is incorrect because we know as a giant star, it contains helium and carbon. And so the first stars were composed of 75% hydrogen and 25% helium. All right. So that's why the correct answer is 4. All right. So number 14, it says, based on the gravitational field model, use the word list to complete the passage by placing the correct terms on the lines below to describe the effects of Earth's gravitational field on the motion of HST and the moon. All right. So we're going to look. Oh, sorry. Here we go. It says, so some key information says the model represents the location of the HST orbit and the moon's orbit around Earth. The moon's orbital distance varies from approximately 363,100 kilometers to 405,700 kilometers. All right, we have the model. And then it says the orbital motion of satellites, natural or human-made, are determined by the strength of the gravitational field at the satellite's location. The model below shows the formula used to calculate the strength of Earth's gravitational field for Earth's satellite. Okay, so they give us this formula. R represents the distance between the two, the mass of the Earth, universal gravitational constant, which is just some number, and we get the gravitational field strength, okay? So let's start. It says compared to the average distance from Earth to the moon, the distance from Earth to HST is what? Is blank. Compared to the average distance from Earth to the moon. So when I look at my model, right? Look at my model. From Earth to the moon, right, in its orbit, right? And I just drew I should draw more of just a straight line, not a curve, right? Um, and I represented in blue, okay? And when I am putting green, the distance between Earth and the satellite HST, and I put it in green. So which one has a shorter distance, right? Or if we look at HST, the distance from Earth to the satellite is shorter. So one of the first things I'm going to see, the distance from Earth to HST is definitely going to be less. Remember, you're writing your responses on the blank space. You're not circling it, right? You're writing it down here. As a result, Earth's gravitational field strength at the location of HST is blank than Earth's gravitational field strength by the location of the moon's orbit. Well, we saw that the gravitational field strength is right here, right? And it represents G, right? Now, we may not know capital G or M, right? But we know that R represents the center of Earth and the center between the center of Earth and the center of the satellite. Okay? So they want to know if we were to compare Earth's gravitational field strength at HST to the moon, well, here's one thing that we do know, right? Even conceptually, the closer an object is, right? The closer an object is to whatever that it's orbiting, the stronger the gravitational force. Do we remember that? So which is experiencing a stronger gravitational force? It has to be the one that is closer to Earth. The one that is closest to Earth is going to experience a more stronger gravitational field strength. All right. So HST is going to experience a stronger gravitational field strength. Now, let's say, for example, you wanted to use this formula, you wanted to focus on numbers, right? We know just working at fractions, the bigger this R number is, the less the whole value is going to be. For example, if you look at 1 over 2, 1 over 3, and 1 over 4, we have 0.5, we have 0.33, right? 1 over 3, and 1 over 4 gives you 0.25. What do we notice when the denominator number gets bigger and bigger? The number gets smaller and smaller. So what do we know when our distance between the two objects get bigger? It's going to make our gravitational field smaller. That's why when we're focusing on the Earth's gravitational field strength at the location of HST, HST is closer to Earth than the moon. So because it's closer, it's going to have a greater gravitational field strength. So all I'm going to do is write greater. I'm not going to write any other words than what has to be on the word list. If you add something extra, you won't get credit. Now, therefore, in order to maintain a stable orbit, the orbital period of HST must be blank than the orbital period of the moon, right? Well, the word period refers to time, right? And we know, even by looking at the orbital period or the orbital time frame, when we take a look, right? HST is going to take a shorter time to revolve around Earth. HST takes a shorter time than compared to the moon. The moon is going to take a longer time period to revolve around Earth, right? So when I'm looking here, it says the orbital period of HST must be less, right? Shorter time because it's closer to the Earth than the orbital period of the moon. All right, let's take a look at 15. Hold on, let me get a second. All right, so 15 says, based on the model and Kepler's laws. All right, so based on the model and from our background information, Which graph correctly represents the relative orbital speeds of HST and the moon as the two satellites orbit Earth twice? Okay. Well, which one is going to have a higher speed, right? According to Kepler's law, if we remember Kepler's law, right? We know that the object that is closer to whatever the object is being orbited is going to travel at a faster speed, right? That refers to Kepler's third law, right? It even refers to Kepler's second law, right? So when I look compared to HST and the moon, HST and the moon, HST is closer to the Earth, so it's going to have a faster speed compared to the moon. The moon is further away from the Earth, so it's going to have a slower speed. So just by looking, what options can I cross out? Right? I can cross out three because right here is saying that the moon's speed is going to be greater than HST, and that's not true. And I can even cross out choice four, right? The speed of HST is going to be greater. Now, what's the difference between one and two, right? For one tells us that the moon's speed is staying the same. It does not change, right? The moon's speed does not change. And here it's saying that the speed does change as it orbits the Earth twice. Now, the only way, and this is according to Kepler's law, the only way that the speed of an object, or let's say the moon, changes is only if its distance is changing, right? So if its distance is changing as it's orbiting the Earth, then your speed is also going to change. That refers to Kepler's second law, right? If we take a look, let me pause right here real quick. All right, when we're talking about Kepler's third law, right? Kepler's third law, here we go. It lets us know that planets move faster when closest to the sun, right? And it also lets us know, according to the note, the speed of a planet changes as it orbits around the sun, right? Why is that the case? It's simply because the orbital speed depends on distance from the object being orbited. That means that as long as the distance is changing as an object is going around the sun, right? Or if it's orbiting another object, then the speed is going to change as well too. So is there any information that lets me know that the distance of the moon is changing as it's orbiting? And it says it right here. The moon's orbital distance varies from approximately 363,100 kilometers to 405,700 kilometers. So that lets me know, if I'm going to erase, that lets me know that there's going to be times where the moon distance is at 363,000, and there's going to be times when the moon's distance is going to be 405,000. If that's the case, then we need to pick a graph that also shows that represent that the speed is changing as it revolves around. That's why we're going to cross out two because it's telling me that the moon's distance does not change as it orbits the Earth, and that is not true. The moon's distance is changing, right? Even here, and I'm not sure if we can clearly see, right? But there's a point where the moon is closest to the Earth, and then there's a point where the moon is farthest from the Earth, right? And as a result, the speed is going to be different. When the moon's closest to the Earth, it's going to travel the fastest, right, in its orbit, and when the moon is furthest from the Earth, is going to travel the slowest in its orbit. That's why the correct answer is choice one. Right. Next question that we see here, right? Basic answers to question 31 to 35 on the information below and your knowledge of Earth and space science. That means the reading passages and the diagrams can be used for these cluster questions. All right. So remember, this is a time test, all right? And if you're someone who is a quick reader, that's fine. But I like to go to the question first and then go back to the passage to see what we need to focus on. So 32 says determine in centimeters. All right. So I'm going to determine in centimeters how much farther away the moon from Earth the moon's average orbit will be 1,000 years from its present day. And explain why this change in distance will not significantly affect the moon's period of revolution around the Earth. Okay, so what are we talking about here? Let's see. All right. So when I'm going my reading, I'm going to highlight any information that talks about the moon's distance, anything that refers to the moon's orbit, anything that refers to the fact that it looks as though the moon is moving away from the Earth. All right. So anything in regards to distance, um, or anything about the moon's average or moon's orbit in general. Okay. So let's see. About 4 billion years ago, the moon was very close to Earth. Okay. So that's something to keep in mind about the moon's distance to the Earth, and Earth may have been rotating at a much faster rate than today. It is estimated that each Earth day at that time may have been 6 to 8 hours long, which, when calculated, would result in an Earth year of about 1,400 days. Remember, I'm focusing on anything that refers to the distance from the moon to the Earth. Okay? The force that causes tides on Earth creates tidal friction, which over time slows Earth's rotation, causing Earth days to become about 24 hours long. Once again, focusing on the distance between moon and the sun, anything that talks about the moon's motion, right? In terms of its moving away from Earth. As Earth's rate of rotation has decreased, the moon has continued to move farther away from Earth. So that's important. All right, at an average rate of 3.8 centimeters per year. So now we know after every year how many centimeters is the moon moving away from Earth. All right, keep that in mind. It says the moon orbits Earth at an average distance of 384,400 kilometers. This might be important as well, too. All right, so that's the distance right now between the moon and the Earth, right? The model and graph below shows some information about tides. So I see some information about tides, see information about tides, but my focus, right, is going to be how much farther away from Earth the moon's average orbit will be 1,000 years from the present day. Well, I know the moon's average orbit, right? The moon orbits her at an average distance of 384,400 kilometers. So I may want to just write that information right here. Okay? And they want to know how much farther away will the moon be in 1,000 years. Well, don't I know the rate each year that the moon is moving? Let's see. It says right here, the moon has continued to move farther away from Earth at an average rate of 3.8 centimeters per year. 3.8 centimeters per year. So every year is moving 3.8 centimeters. So when I'm calculating the distance, I need to ask myself, how many centimeters does it move in 1,000 years? So therefore, I'm going to do the work right above here. 3.8, right, centimeters per year. That's what we learned. And I want to know what my new distance is going to be 1,000 years later. So when you go in your calculator, 3.8 times 1,000, you end up getting 3,800 centimeters. And that's my new distance. All right. Now, what did they say about the explanation? It says, explain why this change in distance will not significantly affect the moon's period of revolution around the Earth. So they tell us it's only going to move 3,800 centimeters in 1,000 years. The distance right now is 384,400 kilometers, right? So we got to ask ourselves, if the moon only moves 3,800 centimeters, is that really going to change this distance as much? When we're talking about 384,000 kilometers, right? Well, even when I take a look, 1 kilometer is equal to 100,000 centimeters. So that even lets me know that 3,800 centimeters, it doesn't even, it's less than 1 kilometer. So the distance changes by like less than 1 kilometer. So will this change in distance not significantly affect the moon's period? Well, we can say, right, the distance change of 3,800 centimeters is very small compared to the 384,400 kilometers. All right. The distance change is very small. Therefore, there will be little change in the moon's period of revolution around Earth. All right. If you mention, just by you mentioning even this part right here, right? And you mention the distance change of 3,800 centimeters is very small compared to the 384,400 kilometers, right? If you're mentioning that the distance won't even change that much to affect the moon's periods of revolution, that would be fine as well too. All right. So, but you want to make sure that you mention that the distance of 3,000 centimeters is a very small change compared to the moon's average orbital distance. All right, so it says the table below shows some information about the sun and moon. All right, it gives us some information about the sun and moon data. Okay. And it says construct the explanation to support the claim that in 700 million years, a total solar eclipse on Earth's surface will be impossible. In 700 million years, a total solar eclipse on Earth's surface will be impossible. Okay? Sorry. All right. So one of the things we need to understand is how does a solar eclipse work, right? We need to understand that. So, we know we have our sun, right? And we learned in class, I'm gonna put M for moon, and we have E for earth. And we know that a solar eclipse occurs when when there's a portion of earth that is covered by the moon's shadow, right? So we have light that goes on the moon, and we know a shadow is formed, right? The moon's shadow, right? This is the moon's shadow. And so therefore, this is the moon's shadow, and therefore, whoever is right in this region right here that is influenced by the moon's shadow is going to see a solar eclipse, right? But according to the reading, what did we learn? If we look back, it tells us that the moon is continuing to move farther away from Earth, right? And we calculated in 1,000 years, right, there's not going to be that much of a difference compared to the moon's average orbit, right? This chart right here gives us the size of the sun and the size of the moon as viewed from Earth. So even though we know that the sun is clearly so much more bigger, right? It's so much more bigger than the moon, but they look to be about the same size on Earth because the sun has a much larger distance from Earth, right? But the problem that is facing is that in 700 million years, what's going to happen with the moon? What have we learned? The moon is going to be farther and farther away from the Earth. So, what ends up happening if the moon is now farther away from the Earth, right? Right? The shadow is going to be so small, right? The shadow is going to be so small now, right? That as a result, the moon will no longer completely cover the sun. Right now, the moon completely covers the sun because the sizes look to be very similar, right? Even when you're looking at the angular diameter, right? They're pretty similar to each other. But as the moon gets farther and farther away from the Earth, this diameter value is going to go down. That means that the moon is going to look even smaller. And for a total solar eclipse to occur, the moon has to completely cover the sun. But if the moon looks smaller and smaller, is it really going to be able to completely cover the entire sun? It won't. It won't. So when it says construct the explanation to support the claim, we can say, right, the moon will no longer be able to completely cover the diameter of the sun. Oops, typo. All right. You could also say, oh, sorry, let me enter. You can also say that the sun will be visible during an eclipse because the moon's diameter will be much smaller. All right. So that's something to keep in mind. We only call it a total solar eclipse, and this is what I'm highlighting. We only call it a total solar eclipse when the moon completely blocks the sun. But the farther away the moon is traveling away from Earth, it's no longer going to be as large as the sun to us. It's going to be smaller. So now, by definition, we won't have a total solar eclipse anymore. Now, maybe a partial eclipse instead. All right, so it says the measured angular diameter of a celestial body is the angle that the diameter of the body makes as seen from Earth. Okay, so that's an important piece of information. So basically, when we're talking about the angular diameter, we're talking about how wide does the object appear. So the greater the angle, the greater the object appears to us, right, in the sky. So based on the information in the table, all right, what table are we talking about? There's only one table, the table right here about the sun and the moon. And we learned some key information about what the angular diameter means, right? It refers to how big or how wide the object appears to look at us from Earth, right? So it says, based on information table, which letter pair correctly completes the passage below? The change in the angular diameter of the moon during the moon's orbit is blank, then the change in the angular diameter of the sun during Earth's orbit. Let's just pause right here. All right. What we talk about by changing, right, in the moon's orbit compared to Earth's orbit? You see the word perigee and apogee, right? They refer to positions when the moon is closest to the Earth, right? When the moon is closest to the Earth, and when the moon is farthest from the Earth. Okay? And that makes sense because when the moon is closest to the Earth, we have a larger diameter. And when the moon is farthest from the Earth, we have a smaller diameter, right? Now, when the Earth revolves around the sun, right? Let's look at the change that occurs of the angular diameter of the sun, right? Perihelion refers to when the Earth is closest to the sun, and aphelion refers to when the Earth is farthest from the sun in its orbit. Okay? So while these two orbits are taking place, let's look, like the problem says, let's focus on the change. All right. So as the Earth goes around the sun, it goes from 0.54 to zero point 0.52, right? And it's going to repeat itself back to 0.54 to 0.52. So what's the change here? Right? If I was to subtract these two, it looks like there's a change of 0.02. What about the change here, right? If I was to subtract these two numbers, and you could pause the video to do so, the change looks to be about 0.07. So, where is there a greater change? It looks like there's a greater change in the angular diameter of the moon in its orbit. So, the change will have to be greater for A. Right? It has to be greater for A. So that automatically crosses out 3 and 1. Let's continue. All right. Because the moon's orbit is inferred to be blank elliptical than Earth's orbit. The moon's orbit is inferred to be more elliptical or less elliptical than Earth's orbit. Well, there's two ways that we can approach this, right? If there is if there is a greater change, right? If there is a greater change in the angular diameter when the moon is really close, when the moon is really close to us, it's bigger, right? And when the moon is farthest from us, it's smaller, right? But we see for the sun, there's not really that big of a change. When we're looking at orbits, right? Elliptical orbit, right? The more stretched out a orbit is, the greater the distance between when a planet or moon, right, is closest to whatever it's orbiting and when it's closest and then when it's furthest, right? So, for example, in what I've just drawn here, when the planet is closest, right, it's a clear difference in the change between when the planet is closer to the sun and when it's farthest from the sun. This is a more elliptical orbit, right? Which means there's going to be a greater change between the diameter that we see when the planet or the object is closest to whatever it's orbiting and farthest. When we have a less elliptical orbit, right? We have a less elliptical orbit. Is there really a difference in distance between when the between when the object is closest to whatever it's orbiting and furthest, not really a big change. So this shows me a less elliptical orbit. Less elliptical orbit. So if there's a greater change in our diameter, there's going to be a more elliptical orbit, which refers to choice two. You know how your reference table can tell you whether it's more elliptical or less? Let's take a look. Let's go to our reference tables real quick, real quick. All right. So information about our solar system is going to be on page 2 of the reference tables, right? And so when we take a look, right, ha- d- the elliptical, right? Elliptical orbits all determined is based on eccentricity, right? So the eccentricity of an orbit will let me know if it's more elliptical or less elliptical. Higher eccentricity, higher elliptical orbit. Lower eccentricity, a smaller elliptical orbit, meaning it'll be more circular. When I look at the eccentricity of the Earth, and I see the eccentricity of the moon, right? Which has a more elliptical orbit, the one that has a larger eccentricity. So this also lets me know how I use the reference tables to let me know that B is going to have a more elliptical orbit. It has higher eccentricity. All right, that's why the correct answer is choice two. All right, have a wonderful, blessed day. Make sure to like, share, and subscribe. Take care.